These are notes from Malham's Math 70 for Wednesday, April the 29th, section 12.3, page 715. Friday, which is May the 1st, you'll be getting a quiz on today's material 12.3 and last time's material 12.2. You'll also be getting a new lesson 12.4, but just want to remind you that we have a quiz this coming Friday. For problem 1, they just asked for the sample space if I toss 3 coins, and we've seen this situation before. So each time it could land on either a head or a tail. So that leads to 8 possibilities. 2 times 2 times 2. The first toss is either a head or a tail, times 2 possibilities for the second head or tail, times another 2 for the third toss, either a head or a tail. So we've done this before. The way I've broken it down is assuming the first toss is a head, so I've got 4 possibilities, head, 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 and below that tail, 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 tail for the first toss. And then the second toss, you've got head, head, heads, tails, tails, head, tails, tails. Just copy and paste that down here. Supposing the first toss was a tail, then notice I just copied directly above. Head, 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 tail, tail, head, tail, tail. So these are the 8 possibilities of what could happen for tossing a coin 3 times or tossing 3 coins once. Same thing. Number 5 is a little bit unusual question, and asked to list the sample space of all states in the United States that begin with the letter A. Some of you have it memorized, maybe you don't. You can look that up. Anyway, there are Alabama, Alaska, Arizona, and Arkansas. Obviously, that's not something you have to memorize. If I give you something like that, it's something that you could easily look up on the internet, for instance, but you wouldn't be held responsible for all the states or anything like that. Problem 7 through 15, it says the Lin family is planning on having 3 kids, and to list the sample space for the 3 kids. If you stop and think about it, it's very similar to the heads and tails here. You're either going to have a girl or a boy. So if you notice what I did here, I just substituted girl for head and boy for T, and everything is pretty much exactly the same. So same logic. The first child can be a girl, so I put G, 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 G. Or the first child can be a boy, I put B, 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 B. Then, once again, for the second and third children, very similar to what I have here, it's girl, 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 boy, boy, girl, boy, boy. Copy and paste that straight down, so notice straight up for the second and third child, G, 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 B, B, G, B, B. So these are the possibilities that could happen for 3 children. You have 8 total possible ways to have the children, and here they are. Problem 11 asks for the sample space of having at least 1 girl. Having at least 1 girl, it's probably easier to say, well, what's the situation of no girls? Well, that would be all boys, so boy, 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 which means 7 out of 8 would have that. So I just copy all of this and just eliminate that last one. So if you notice, I just copied the first 7 here, G, 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 B, all the way to boy, boy, girl, and just threw out the last one. So all of these possibilities, if you notice, there's at least 1 girl in each of these situations. Now 13 asks for the probability for at least 2 girls. So at least 2 girls means either 3 or 2. So 3 girls means G, G, G. 2 girls, there's 3 ways that could happen, and it might be easier to think of having the 2 girls, just think of where the only boy can be, or the only boy can be the third child, the second child, or the first child. So GGB, GBG, or BGG. So there's 3 ways that can happen. So the grand total of having at least 2 girls is 4 out of 8, which is 1/2. Okay, so nutshell, if you have 3 children, the probability of having at least 2 girls is exactly 1/2. And then 15 asks for the probability of at least 1 girl. Well, we just did that from over here. There's 7 possible out of 8, so 7 out of 8. So let's say if a couple wants to have at least 1 girl, but have exactly 3, then the probability of having at least 1 girl is 7 out of 8. All right, for 16 through 18, you're tossing a coin 4 times. That means there are 16 outcomes that are possible, because the first time you can have either heads or tails. Likewise, second time H or T. Likewise, the third toss and the fourth toss. So there's 16 possible ways that you could have an outcome if you toss a coin 4 times. And back here, problem 1, you were only considering 3 tosses, so there's 8 possibilities. All right, they're asking for the probability of having exactly one head and three tails. The easiest way to list all those possibilities is to just say the head can be the first toss, or the second toss, or the third toss, or the fourth toss. And once you have that location, then just put T's for all of them. So here the first toss is a head, then I just put T, T, T. Here the second toss is a head, then I put tail first and third and fourth. Likewise here, head the third toss, so T, T, and T. And head is at the end, tail, tail, tail. So that's 4 out of 16 possibilities, so 1/4. So in a nutshell, if you toss a coin 4 times, the probability of having one head and 3 tails is 1 out of 4. Okay, then for 19 to 22, you have a 12-sided die. So 12 sides, 1, 2, 3, 4, up to 12. What's the probability of landing on the number 12 itself? Well, that's 1 out of 12. And that would be likewise a possibility for any particular number. What's the probability of landing a 7? 1 out of 12. What's the probability of getting a 3? 1 out of 12. All the numbers are there from 1 to 12, assuming they're equally likely. Each one would have a chance of landing 1/12 of the time. Problem 21 asks for the toss to be divisible by 4. Well, divisible by 4, that's 4, 8, and 12. That's 3 chances. So you have 3 chances out of 12, which is 1/4. Then 23 to 33, you have 2 dice that are rolled, standard dice, 6 pips each. And so that means for standard dice, where you can get a 1, 2, 3, 4, 5, 6, there are 36 outcomes possible. You have 6 choices for the first die. You could get a 1 through 6, 1, 2, 3, 4, 5, 6. Likewise, 6 tries for the second die, 1, 2, 3, 4, 5, 6, for a total of 36. You could theoretically write them all out. The text actually does that. So if the first die is a 1, the second one can be a 1, 2, 3, 4, 5, 6. So you get 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Likewise, for the first die, the toss could be a 2. Then the second one can be 1, 2, 3, 4, 5, 6. So 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Likewise, 3, 1, and so on. All the way down to the first die being a 6. You get a 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. So you have 6 times 6, or 36 total possibilities. All right, so 23 asks for a sum of 6. So how can you get a sum of 6? Well, the first die can be a 1 and the second can be a 5. Or you can have the first die be a 2 and then the second is a 4, or 3, 3, 4, 2, or 5, 1. So that's 5 out of 36. So your chances of getting a sum of a 6 is 5 out of 36. 25 asks for the sum of 2 possibility. Well, the only way you can get a 2 is a 1 and a 1. That's over here, so that's 1 out of 36. 27, how can you have a sum of 1? There's no way you can have a sum of 1. The smallest you can get is a 2. The lowest you can get is a 1 and a 1. So what's the probability of landing a sum of 1? That would be 0. 29 asks for the sum being at least a 10. At least a 10 means 10, 11, or 12. So how can you get a 10? Well, you can have a 4, 6, a 5, 5, or a 6, 4 for the first and second die. Then how can you get an 11? Either a 5, 6, or a 6, 5. And how do you get a 12? The only way is a 6 and a 6. So what's the chances of getting at least a 10? You have 1, 2, 3, 4, 5, 6 out of 36 total possibilities, or 1/6. So your odds of getting, or the probability of getting at least a 10 is 1/6. 31 is a little bit more involved. So it says to get an even number. So even numbers are 2, 4, 6, 8, 10, and 12. So we list the possible ways of getting each one. So what's the probability of getting a 2? Well, the only way to get it is a 1 and a 1. So there's only one way you can get that. How do you get a 4? 1, 3, 2, 2, or 3, 1? There's 3 ways. How do you get a 6? 1, 5, 2, 4, 3, 3, 4, 2, or 5, 1? That's 5 ways. How do you get an 8? 2, 6, 3, 5, 4, 4, 5, 3, or 6, 2? That's 5 ways. How do you get a 10? We just did that. 4, 6, 5, 5, or 6, 4. That's 3 ways. And the only way to get a 12 is with a 6 and a 6. So we add them all up. 1, 3, 5, 5, 3, 1. That adds up to 18. So 18 out of 36 total, which is 1/2. So the probability of getting an even number is a half, which is kind of logical. That means the probability of getting an odd number is also a half. Finally, for 33, ask what's the probability of getting doubles. Doubles means you get the same number. That is 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, or 6, 6. Well, that happens 6 ways out of the total of 36, or 1 in 6. So the probability of getting doubles is 1/6. Okay, so these are notes for Math 70, Wednesday, April the 29th, section 12.3, page 715. So next time, Friday, May the 1st, you will get a quiz on today's stuff, 12.3, but also Monday, 12.2, and we'll also go on to 12.4.